Okay, sorry for the delay. So right now, today I'm gonna. So first of all, let me introduce myself. My name is TT Wong. So starting from this week, I will be giving the lectures for FIT 5221, and so you can just call me TT. So in case you have any questions during the lecture, just feel free to voice out or write it down in the chat box. Okay, let's start with today's lecture. And the topics I'm going to cover today is the adversarial machine learning and vision transformer. So let's start with the adversarial machine learning. So I think in the last few weeks, you have already learned some of the new deep learning techniques that use for classifications to classify image or even classify or doing segmentation on that. So they are mostly based on CNN, and and no matter what kind of deep learning you're using, you always have some problem. So even though today we have already a very high success rate, so for example, like the ResNet for image classifications, today we can achieve up to more than 90% of success rate. So that means we have a very high success rate. There are still some error you can see from these statistics. And some of them are due to the what we call the adversarial example. What are they? So it has been found that, for example, I take this, let me just turn this into a laser. For example, if I take this panda image, for human, you can easily identify that it's just a panda. And for machine with sufficient training, the machine will be able to classify as a panda. But this has been found that by adding some kind of perturbations, that means or noise, for example, what kind of noise? For example, if you pick some of the pixel in the image and push the value down or up, just a slight modifications of the value deviated from the original image. You can take many point in these pictures and do this kind of what we call perturbations, or you can just call it adding noise into it. So you can obtain another image on the right hand side, which is for human is still a panda image. We can't tell what is the difference between this left and right. But for machine, it turns out you can fool the machine, fool the model you have trained for image classifications, and they misclassify this panda as something else. And we call this kind of example, this kind of image, that with certain perturbations, we call them adversarial example. And this, you may ask, how come we have this kind of adversarial example? It can be intentionally created, just want to attack our classification model, or it can also be unintentional. One classical or typical case that can generate this kind of noise in your image is, I think everyone will use it. Just do this. Where's my pen? Over here. Okay. One of the classical error or noise injected into the image is JPEG. We probably use every day. And because the JPEG, so this is called some kind of JPEG noise, because JPEG is actually a lossy compressions method. That means the restored image from a JPEG compressed image file will actually deviate from the original image. So I can show you some example that you can even see the visual difference. So this is the image without any compressions. This one. This particular one, you can see that there are some artifacts around the edges of the image. And this is usually called a raining artifact. So Can you see that? Can you guys see the difference? Just want to make sure there's no compression error due to the zoom. You can't see that? No. Let me just swap between these two. This one is original. This one is the one with ringing artifact. Can you see that? Can I see the slides? Oh, sorry. I think I have shared the wrong. Give me a moment. I should share my screen. Okay. Sorry about that because I swapped the window. So this one is the original. And this one is the one with artifact, with the JPEG ringing artifact. Sorry about the mistake. So this for not sharing this full window. Just give me a second. I need to drag the title bar. So now you can see JPEG is one of the most or common way that is not intentional, but it is one example that you can inject noise into your image without knowing it. Just walk back to the PowerPoint. Okay, this one. So it may not be a big problem that a machine maybe classify Panda image, but it will be a big problem if your model is used in auto driving and it is used to classify what kind of road sign it has seen. So, for example, in this example, if you misclassify stop sign and something else, that could be a big mistake or generating a car accident. So this is why we need to study or understand what is adversarial machine attack. So before that, let me just formulate this in a more mathematical way. So here is, for those of you who are not comfortable with the equations, no worry. I'm going to go through that with you. So the idea is like this. So we can think about the original image, let's say the input X, or for example, in this case is a cat. And this ball, this is a small neighborhood representing a small neighborhood, which is very close to this image, but slightly different. So you can say this is a neighborhood. You can call this as a neighborhood. Okay. So the perturbations or slightly different image are very similar to the original one. Let's denote it as a x pi, and it is still within the small neighborhood from the original image. So within a range, and this range is epsilon. So how is mathematically you can represent an image? So you can understand, you can regard this image. So this X is the image, and you can actually linearize into a vector. One way to do it is simply taking rows of them and concatenate them together, form a vector like this one. So it's actually a vector. It's a very high dimensional vectors because each pixel is an element in this vector. So you can always measure a slightly different image. You can measure the distance within the bound of epsilon. And there can be many of them. And so what is an adversarial example is that it is still an image slightly deviated from your original one by maybe some manual handcrafted noise or some unintentional noise by JPEG. And this creates you another point, another image which is we denote it as xvat. And the difference is the original image, you classify this as a cat. But this adversarial example, you misclassify it as something else, for example, a dog. So this is what we call adversarial example, and it is still within this neighborhood. Okay. So there are some more mathematics, so don't worry about that. This is just repeating what I have just said with some mathematical notations. So these are the one I said, the cat. And this misclassify the label, for example, a dog. Okay, so what are what are this complex notation it means? So if you remember, this is just a model weight. That means after training, you have some kind of weight for this model, and this is the input image, which is the original cat image, and this guy is the prediction score. And what are these complex ones? It's just trying to find. So this is the class. Okay, you have M class, for example, dog, panda, pig, whatever. And then you want to select one of the class I that can maximize this prediction score. Okay, so that's the idea. You want to maximize. So basically what it said is the best predicted class the model can give you. Okay, so for the original one is the cat. But if you give this model, the same model, with the adversarial example, it will misclassify. Best it can do, it will misclassify this adversarial example as a dog image or something else, just other than cat. So that's the idea. So these are just mathematical formulations of what I have just said. And obviously, it would be the best if you can train a model that can always any point, any image that are very similar to the original cat, and within this bound, all this stuff, you can classify them as cat. Okay, so that's the best case. So mathematically, it's just like, oh, I want this the ground truth is a cat. I want everything in this neighborhood will be classified as cat as well. So that is what it said. Unfortunately, that is in reality is not the case. In reality, we can easily find what we call adversarial example. That is some image which is still very close to the original one, but you will misclassify it. Okay. So we need to understand. So obviously we want to train a model to be robust to this kind of what we call the adversarial attack, because you can call it an attack your model classifications. So we need to understand what happened in this kind of adversarial example. What happened? Why this misclassification happened? So one way to do it is that we can visualize the label map. So the map of label surrounding the original, let's say the cat image. Okay. So let's say we can plot a map. So any point in this image is corresponding to a slightly different versions of the cat image. Okay, is that clear? And then you will ask, what are this color? So this color, they are just the label map. So let me just write it down here. So let's say these blue regions here, this blue one, is the cat label. Okay, the cat label. So for example, this guy, this orange area is the dog label. And this red one may be monkey. And this yellow guy may be something like let's say even we can call it dragon, whatever example can be even not something real. Okay, so this map basically tells you even within a small label group, the label will suddenly change. Okay, this change will especially significant along certain directions. So let me just remove all this label. So the reason we got a misclassification within a small region is that it could be the case that you train up a model that give you this kind of label map, and a small motion, small move, or small deviation from the original, just a slight move, let's say along this horizontal line, you will see there's a change from one state to another. Let's say in our previous example, we call this red region, this red part over here is a monkey, or let's use the dog. Again, let's use the dog. We call this dog, this region, this red part. I think it's over here. This red part is the dog. Okay. So just a slight change, you can cause it misclassified. And this is why you will see something like you will see this misclassification because the label map changed so suddenly, even in a short period of regions. Okay, then you may ask, is it just an illustration? Is this map is just an illustration? In fact, we can construct a real one. We can visualize a real label map, and there are some complex notation here. What are they? It has been found that the label will likely to change more vigorously, suddenly, or drastically if you move along one particular directions. And this is the gradient. Gradient directions. What are this? So let's go back to the notation definitions. So if you still remember, the X is just an input image, and each element is just the original pixel. So what this map is, how this map is plotted, it is actually a map that take the gradient of what? Gradient with respect to the change of pixels. What does that mean? That means if you modify, so for example, if you take your cat image, and you take one pixel of them, let's say you take this particular pixel, you take this, let's say the original value is 0.5, you modify it to, let's say 0.5001, something like this. And obviously, if you give this new modified image to the, let's say to your model, and it will give you a new predictions or classifications results, let's call. And it may still stick to cat. It may still change to something else, but it will certainly give you a different value prediction score, which correspond to the loss. And so you can form a vector by creating by taking the partial derivative. So every pixel can change, and each small change will cause a change in your loss. So you can take this to form a vector. This is called a gradient. Okay. So there are also, unfortunately, I need to explain this complex notations so that you will not be afraid of that. So let me just go into details. So if you take this is the prediction result, prediction label. And this is the true label, the true ground truth. Okay. So there could be a difference between these two. So you can compute a loss between your predictions and the ground truth. Usually it's the cross entropy loss. And the gradient of that is just for each small change in your pixel value, what will be the loss? What will be the loss change? Okay, so you can form a vector like this, and this is the gradient. And we know that, mathematically, we know that if you move along this gradient, if you move along these directions, it will cause you the biggest change in the loss value. Okay, so what does that mean? That means this moving along the G will probably give you a largest change in loss. And it will have a higher chance. I didn't say it must, I just say it more likely. Okay. So this is just just what we have seen. And let me just show you this. So you can actually plot the loss. You can plot this. So this direction is the loss value. So you can see that we can actually plot, if you move along the G, which is, it will always get you the steepest change. So you will climb up this loss mountain. So these directions basically tell you where is the steepest change in your loss value. Okay, so this is the meaning. And we believe it's not always, I have to emphasize, it's not always, but it will have a higher chance with this large change in value, the label will probably change rapidly. And this is why usually you will have this kind of sudden change in label in a very short distance, because the change of the loss change is the much larger. Okay, so that's the idea. So basically, the way that to attack, to create adversarial example, is to somehow move along the gradient directions. Okay, so that's the idea. And you may ask why, so some details about how this, if you are interested to know how this is plotted. So this doesn't matter, it's just some directions that is orthogonal to the gradient directions. Okay, so because it's a high dimensional space, if you can find any vector, any directions that are orthogonal to the gradient, and you can take a cross section of that and to find the label map like this one. Okay, so it's just for the basic idea of this diagram is to tell you the gradient directions is usually the directions that would give you the higher chance of changing the class label during the predictions. Okay, so if you agree with that, and this is what the field has been believed, what we do is that we need to, before I continue, let me just show you this. So this is another notations to help you understand why this gradient give you the largest change. So if you remember what this equation is, so this is the true label, this is the predictions, this is the ground truth, and this is the loss functions. What you do if you add a noise or perturbations to the original image. Okay, so that means you inject some noise into it. And mathematically, you can do Taylor expansions. I hope you understand what is Taylor expansion because we don't have time to go through it. So you can approximate by expanding this guy on the left can be approximated by the original loss functions plus the first term here. And of course, there are more terms at the back, which is less important. First term is the most important one because it's heavier in value. And you can see the first term is actually evolving the gradient. So that means a slight change in this can be roughly approximated by a component that corresponds to the gradient. And this also tells you the gradient is the most important term that will contribute to the deviations of the loss. Okay. So it's just a small proof why gradient is so important. So then if you agree with me that the gradient direction will give us a higher chance for misclassifications, then the next question is, maybe we should learn or just study how to create adversarial example. Because by creating them, we are able to better train our model to be robust to this kind of attack. Okay, so how to train what kind of attack we can create? So there are actually two kinds of attack goal. One of them is that untargeted attack. The other is called a target attack. What are they? Why are they look so complicated? So the untargeted attack, this one, is actually, for example, if your original ground truth label is the cat, so you want to create some adversarial example which fool your model to misclassify it as something else. For example, a dog, a pig, or a monkey. Anything except cat. So it can be anything. So it means untargeted. That means anything here. I don't care what misclassification is. I just want it cannot be the cat. Okay. So the targeted attack is that I want to design an adversarial example. Let's say the original is still the cat, but at this time I want it to be misclassified as dog. Okay, so I want only this one, only the dog label. I chose this wrong label, and please create an adversarial example that always misclassify stock. Okay, so this is called a target attack. So there are two goals. Okay, so you can express once you have a goal, you can formulate it as equations. So if you are talking about untargeted attack, that means I don't care what mislabel it is, just not the cat. So if that is the case, it is equivalent to say I want to create an adversarial image that always create the largest loss. So to maximize the loss. So this the ground truth is the cat. The ground truth is the cat. I want to create a deviation in terms of loss. I want the predictions to be moved away from the cat. And this can be written as maximizing the loss. So I want to find an image, a deviated image, or image with perturbations within a small neighborhood of this original cat image that can maximize the loss. Okay, so this is the goal if you are talking about untargeted attack. On the other hand, if you want a target attack like this one, so that means you want a particular wrong label, let's say the dog. So let's say this guy, so you will have a different goal. The goal is something like this. You want to target to a dog label. Okay, So this is the doc label. Okay. And you want your predictions to be as close as possible because you want to minimize the difference from your prediction to the doc. Okay. You want to find the image within your small neighborhood and you want the predictions to be misclassified as a doc. So that's why you want to minimize that. So that actually, if you write the goal in a mathematical form, they are slightly different. Okay. No matter which one which goal you want to do, it doesn't matter because there are three different methods, and three different methods can all be used to do this untargeted attack or targeted attack. So here I want to show you how we do it. Okay, so it looks like we have a very complicated pseudocode below. There are three methods. I just want to highlight this. Right. So one is the fast gradient signed method, in short, FGSM. The other is a projected gradient descent, and one is the momentum iterative method. Okay, don't be scared by this complex name notation, these terminologies. So they are just some method to do what we want to do. So remember, we want to, let me just do it again here. So now let's start with the untargeted attack, okay? So to do so, we want our predictions to be as far away as possible from the ground truth. Okay. We want to maximize the loss away from the ground truth. Okay. And still within the neighborhood. So what does that mean? So let's say I have this neighborhood and X is the ground truth, the cat image. So one way to do it is that as I said, the gradient directions probably give you the largest change in the loss. So we'll move along, not exactly, but close to this directions. And in one step, I want to push this. I want to create the adversarial one that are at the boundary of this neighborhood. Okay. So this is one step. So that's why in this first method, what it do is that it take the original cat image, modify it by adding some noise. And if you look at this is the distance, the radius, if you are norm 2, the epsilon from this is what we define the neighborhood. So we want to put it at the boundary of this neighborhood and along a directions, which is this one is the gradient. This one is the gradient, okay? But instead of directly using the gradient, because the gradient is not normalized, and we'll take this form, okay? We'll compute an element-wise the sign vector. So this will give you a vector. It was slightly deviated from G, but it doesn't matter, but it's close, okay? In these directions. So that's the idea. I just jump one step to create the adversarial example by putting it at the boundary of this neighborhood. So that's the idea of the SGSM. Then how about the next one? The next one is slightly different. So instead of one step jumping to the boundary, we are going to move by small step within this boundary. Okay. And we start by, where's my pen? Oh, sorry. I changed too fast. Control P. So Control P. Where's my pen? That's strange. And use this. Okay, instead of one step going to the boundary, we'll move along the gradient, more or less along the gradient by small steps. And then probably we'll reach this point at the end. Okay, so you may ask why the gradient direction will deviate, will change over time. So first of all, let's choose a small step. So this notation indicates small steps. And when moving along the gradient, then you may ask why this gradient will change. The reason is we are using the current locations, the xt, as to compute the gradient. And at different point, the gradient will change because the gradient surface for different neighborhood image may not be the same. So you will see a change in these directions. And hopefully we'll find some optimal one. And here in this particular example, it just has a fixed number of steps. That means, for example, you walk 20 steps, within this neighborhood to find the array survey example. So this is what PGD do. How about the last one? The last one is I think some of you may argue, why should we have this sudden change of directions? So the last one is actually designed according this way. So you want to reduce the change in directions somehow. So instead of moving so suddenly, turn 180 degrees in directions, maybe we can design a method that are producing less directional change. And this is done through these equations. So this V is the last step, for example, this directions. So sorry, should be this one, VT. And the new direction should be contributed both by the original directions and the current gradient. Okay, so we will smooth out the direction change during this iterative step. So that's the idea. So basically, these two are very similar. The PGD and the MIM are very, very similar. You just want to smooth out the directions, just sudden change of directions. So I think for all of you, you should go back to go through the steps in detail. But the idea, I think I have already described it. The general idea and the intuition has been described by this very simple diagram. Okay, is that clear? Let me just check the chat box. If you're not clear, if you want something, you want to ask, just ask now. I know that some of you may have questions. Just feel free to ask. I don't hear any questions. If no, let me just continue. You can always ask. You can come back and ask the questions. Don't worry about that. Okay, so we have the targeted, untargeted attack in this slide. As I said, the targeted and untargeted, they are very similar. It's just the difference of the goal. They're only different by the goal. So this is why we'll have this green highlight, the change of the goal. The change of this goal will change your pseudocode as well, because this time we are not targeting away from the ground truth label. We are targeting from one particular wrong label, and this is why we want to reduce. We don't want to move away from this ground truth, not ground truth, from this wrong label. We want to move closer to this wrong label. So that's why we changed this, modify the code by just modifying two things. One of them is the wrong label. This time we want dot label, and We want to closer, so it's a negative sign. Okay. So if you look at that, all this change or all this modification of the code is due to the goal has been changed. And these are the slight modifications you want to do if you are targeting one particular wrong label, let's say dog label. Okay, so now we know how to create this adversarial example. And once we have this method to create the wrong label, or giving us a higher chance to create a wrong label, then we will be able to modify our model training so that they can be robust to this adversarial attack. So how do we modify our training? If we want to train the model to be robust to this kind of adversarial attack, any suggestions? I'm sorry. You can raise your answer. You can write your answer in the chat box if you don't want to voice out. So if we know, now we know we have the method to create an adversarial example. How do we modify our training so that our model, our classification model, will be more robust to the attack? How do we do that? I have the equation here. I have the optimization code here. But what is the goal? What is the intuitions of these modifications? How do we modify it? In one sentence. Exactly. Train our model with adversarial example. So how do we train that? In one sentence, you can also say it this way. Control P. Okay. So that means we should include the attack during training. If we know that we're probably going to be attacked by this adversarial example, we should simulate. So a better word should be simulate. We can simulate this attack during the training. And this is exactly what this left equation are saying. So if you can see this equation, this is trying to maximize the loss. That means it's moving away, hoping to moving away your predictions from the ground truth. For example, this is a cat. Okay, the ground truth. This one. Okay, so you move away. So this is so you can, if you look at this is an untargeted attack goal. So we want to we'll modify our training goal to something like this. We want to maximize the loss in the inner loop, maximize it so they deviate away from the ground truth label. But at the outer loop, we want to minimize the average loss. We want to train a model. So you can see here, we want to train the model. That means we find a model weight parameters that can minimize the average loss. This is expected value, average loss due to this. So this is what we are doing. We assume there's an attack during the training, and then we want to minimize the average loss. With this in mind, with this attack inside our training. So the implementation is very simple. We just do what we have been doing before. We have different number of epochs And during this epoch, we have number of iterations. And during each iterations, we take a mini batch, which there will be the input image and the ground truth label, something like here. And then we want to for each pair of them, we want to find the adversarial example using PGD with the untargeted goal. So we want to, for each of this example, we want to find the adversarial example to attack our training. And the training loss function will slightly modify. This is the original. We add an extra term. Okay, this extra term is basically the adversarial as input, adversarial example as input, and we want to calculate the loss, how it deviates from the ground truth. And so this is the modified objective functions. And that's it. We include the adversarial example or its adversarial attack inside our training. And we want to minimize the total loss, the average loss, through this iterative training and find the parameters that can, hopefully we can find the optimal one. But as you know, all this, we may not be able to get a global optimal, but we hope we can find at least the local optimal. Unfortunately, I have to tell you the facts that usually the attack is still stronger than the defense. We can always find some adversarial example that can attack our model easily. And this is the reality. So there's no single method that can always defend our models from this adversarial attack, but we want to make it relatively robust. So here I want to show you one result. Let me just take away all this markup. So after training, so let's say this loss function, something like this. Something like this. This is a loss surface, just like what we have drawn here, this one. So, and we all know that the nasty directions that will cause us misclassification, more likely to cause a misclassification, is go along this gradient, because the gradient creates the greatest change in the loss functions, right? So if our model can successfully reduce the average loss due to adversarial attack, what would you expect this surface will change to? So because we know that the cause of the major cause of this is the large change in the loss. So you will be likely, if we are able to train a more robust model, the loss functions surrounding the X will be flattened, because it doesn't create a very steepest change in the loss surface. So hopefully we can create a smoother or flattened loss surface generated by the model that we have been trained for this, what we call the adversarial training. So it will be likely turn the loss function into a flattened one. But unfortunately, I still have to claim that this kind of adversarial attack is not 100% proof you can be avoiding from this adversarial attack. So this is the reality. Okay, I think we have finished adversarial machine learning, and it is the right time to take a short break. So in case you have any questions, I think I will take your questions and try to answer at this moment before I move on to the next topic. And I think I would suggest to have a few minute breaks from now. If you have any questions, just feel free to put it in the chat box and I will answer after the break. So let's break for 5 minutes from now. So we'll come back at 11:02. or 11:03. We'll come back at 11:03. So let's take a break here. Just feel free to put your question in the chat. Okay, let's come back and continue the lecture. So far I didn't receive any questions from the chat box. So I will continue. I assume there is no questions. So again, if you have any other questions, just feel free to ask later. So the second topic I'm going to cover today is the vision transformer. You may ask why suddenly pop up in new terminologies. So the key thing here is transformer. So let me turn highlighter. The key thing here is we want to introduce you the transformer, which is the one of the recent breakthrough in the machine learning. So before the proposal of the transformer, there are we have most of the deep learning techniques being used is CNN based. So we have a lot of the techniques for using for classifications as well as image generations. A lot of them are based on CNN. For example, the GAN generative adversarial trick network. Those are based on CNN. And I think one of the key breakthrough in the past 10 years is this transformer. And in the, I think many of you probably have taken course that teach you what is transformer before. But here I want to, in this course, we will tell you how transformer is used in image applications. In particular, is vision transformer. Okay. So this is why we come up with this vision transformer topics, because that is probably the first image application we're going to talk about based on transformer. So first of all, we need to understand why we have this transformer being proposed. So so as you know, the transformer is proposed for solving NLP problem that means solve the linguistic problem. So for linguistic problem, um, like attacks, those kind of translations stuff. So these are based on a sequence of words. So it's a kind of a sequential data. And unfortunately, CNN by itself is not good for tackling sequential data. And the way to solve it is something like the RNN, recurrent neural networks. So your different sequential data, x01, x02, x0t minus 1, x0t, etc., etc. So this input will be input into this recurrent neural networks, which have a recurrent state like this. Okay, and the period state will base on the current state. Let's say this guy will be based on the previous state value using some equations like this. Okay, so this is how they deal with the sequential data using RNN. But the RNN, unfortunately, we'll not talk about RNN today, but we will talk about why people want something new to over. Why is that? Because there are problems with the solution at that time. Because RNN has limitations. One of them is the vanishing or exploding gradient problem. So if you remember, it's not this one, sorry, Control P. Okay. So if you remember during the training, we need to do the back propagations, trying to speed up the event to find out the best parameters. So the backpop will basically going from one state, going back all this way back. Okay. So if this guy, if the value is bigger than one, it will as you go backward, it will grow. The gradient will grow. If this guy is smaller than one, if you continuously go back, the gradient will shrink. That is why we have a vanishing gradient problem, or exploding gradient problem. Okay. So no matter it's either bigger than one or smaller than one, it causes problem. So this is the one of the problem during training. The other is if you want to depending on the long term, for example, this guy wants to depends on something over here. It sometimes is difficult to capture this long term dependency. The final difficulty is parallel training because you can see you have to do this. The current step will based on the previous step. So that means it's not good, or actually you can't do parallel computations. So this is why this is no good. And it's also why we have this transformer. So the original goal for transformer is to handling linguistic problem. So this keep in mind of that. So that's why we're going to use linguistic example as a start, but I will also tell you how you can apply on image. So let's talk about transformer. So transformer, as I said, is just proposed within the 10 years. So it was proposed in 2017 inside the paper called Attention is All You Need. Okay. And by the Google to solve the NLP problem, as I said. And one of the key contributions of this work is the self-attention mechanism, how they calculate what they call the self-attentions, or you simply call it attention mechanism. Okay. And this is very important because this transformer or this attention mechanism became the driving force for today's generative AI. So a lot of the, let's say the ChatGPT is based on that. So the breakthrough of ChatGPT more or less is because of the transformer, because of this attention mechanism. And also, as well as some of the today's image and video generations, they are also using transformer and attention mechanism as the key building blocks of the generation power. So this is important, and the advantage of that is that this mechanism can enable parallel computing. So because it's not something like the previous one sequential approach, and parallel is one thing. The other major advantage is long range context. Long range context. So that means you can. So for the case of image, let's say control P. Okay. In case of image, if you remember, in CNN we are applying the convolution kernel over a region, which is more or less a local one, right? In CNN. While so this will give you some problem is that if there are something, let's say there's a flower on the left-hand side of the image, and there's another flowers on the right-hand side, bottom of the image. There are some distance between them. So this have a what we call a long-term distance. Let's say the distance between this. So in CNN, you can still associate these two flowers through a sequence of downsampling and this local receptive field. You can still associate that, but it's not that. I would say is not that effective or efficient. In the transformer, because of this approach, this long-term, this self-attention approach, I think the key is because of this attention. Because of this self-attention approach mechanism, it allows you to more effectively to associate even they are far away from each other. Okay, so this is one thing I think transformer is important because comparing to the CNN mechanism. I will tell you more about this later on. Don't worry. So the original transformer architecture is actually drawn over here on the right hand side. For here, it has two parts. This is what they call on the left part is called the encoder. Okay, you see this encoder decoder which repeatedly used in different architectures. So in this transformer mechanism, they call the left hand part as the encoder and the right hand part as the decoder. Okay, and for both of them, you see this attentions. So don't worry about the multi-hat, just focus on the attention. This is the key. Okay, this is the key. Both of them contain the attention mechanism. And in fact, whether we should have both of them, the encoder or decoder, it depends on your applications. Sometimes it doesn't matter, and sometimes actually people change. They all call transformer, but they have different variants of them. And so, for example, some of them only contain the encoder, like BARC, which is a kind of a text encoder, and also the VIT, the vision transformer, we are going to talk about very soon. It is also an encoder only transformer, which means they don't have this. Okay, it's only the left hand side. So on the other hand, there are some of them, some of the, let's say GPT, they only contain the decoder side. That means there's no encoder like this. Okay. And there are also other applications which have both of them, like BARC. Okay. This one is also used for linguistic, for a translation purpose. And it actually depends on your applications, and there are other variants. There are other variants as well. So the architecture on this encoder and decoder sometimes change depending on your application, and also depending on the designer. So it's not a strict rule that we need to have an encoder or a decoder in order to call it a transformer. Okay, there are a lot of variants. Okay, so even though the transformer is proposed for NLP problem, today's a lot of vision problem, let's say image classification, like the vision transformer we're going to talk about, is designed for classification purpose. And we also have image and video generations, like what? Like diffusions. Like diffusion models, they now also use transformer as one of their basic mechanisms. So it sounds like there are many variants of transformer. But what is the key thing in this transformer? As I said, the key thing is this, is the attention mechanism. So let's talk about, so the encoder decoder of the transformer doesn't really matter. The focus is the attention mechanism. So what exactly is the attention mechanism? I think some of you may have already learned it, but here I still want to emphasize the key concept here. So if you remember, the title of the paper proposing transformer is called Attention is All You Need. And I think this is the best title because they are really telling you the truth. It's not the transformer architecture, it's actually the attention mechanism is all you need to know, all you need to learn. And this is the core. And the core of this so-called self-attention is this Q key value design. What are they? So you can sometimes, in short, it's just called QKV. So the query, so it means this mechanism can involve the query, the key, the value. Okay, three components. So by looking at the name, it's something look like a kind of a table lookup. So query is something you're searching for, and the key is the index entry in your dictionary, for example. And the value is the definitions of the key. Okay. So it's like you want to look up the meaning in your dictionary. Okay, let's take one example. Let's remove all this. So for example, if you have a sentence like this one, it said the animal didn't cross the street. I will use the linguistic example because it starts with linguistic. The animal didn't cross the street because it was too tired. Okay. So here we want to understand what is it, what it refer to. So is it referring to because this word? Doesn't look like. Is it referring to the street? Maybe. Is it referring to there? Or is it referring to cross, etc.? And is it referring to animal? So this is probably, for human, we can easily tell is very likely because we know it's a tired. Because the street will not be tired. So that means there's a concept. This is related to something live, living stuff, right? So if you look at this sentence from the aspect that anything that is living, from the aspect, from the perspective, living stuff perspective, that is something you look at the problem. Is there anything that is living? Okay. So in this case, we can tell the best meaning, the best option, associations with this it is animal. Okay. So in other words, we can think it this way. This time the query is it, what it refer. And the keys to search every word in this sentence is the key inside the dictionary we want to look up. Okay. All the words in the sentence. And the match one, the match key is the animal because you have some living characteristics. So the value is what? The value is not just saying, not just the meaning, the dictionary meaning of the animal. It's actually the contextual meaning because it is something that lives, something that can tie it, something like this. Okay. So this is why in this linguistic example, you see why it can be applied. So in other words, this mechanism, in this QKV mechanism, what we want to do is to retrieve the relevancy, how relevant each item associated with the others. Okay? We want to determine the relevance. Relevant in terms of what? Because when we talk about relevance, it must be in terms of something or from what we call from one perspective, from some perspective. So here I give you two sentences. They look very, very similar, except the last word. Okay. Except the last word. So keep in mind of that. So if you are talking about from the living perspective, something living, and because it triggered the tired with the tired, so this it will be more associated with animal. On the other hand, if you have something with spatial perspective, that means something related to spatial relationships, the size, the distance, the orientations, this kind of perspective. If you are considering the meaning from this perspective, now the why will trigger this, right? Because when you talk about the why, it's something related to spatial. So the street will be the best associated or relevant, most relevant. Right? So in other words, it really depends on what perspective, I always use this word perspective, you're referring. And this perspective is application dependent. That means for different application, you probably have different perspective to look at. And in other words, you can translate that related to a particular deep learning applications. Okay. And also that can be related to your objective, how you design your objective. Of course, we are not going to talk about this kind of so specific kind of design of the objective functions. We'll have a more general design of the objective function, and the mechanism and this self-attention mechanism will automatically find out what perspective to look for. So that's the idea. So let me just briefly introduce how it works. So again, we'll stick to the linguistic example. So these are words, okay? So in the NLP applications, a token can be a word, for example, like this, and can be a subword, depending how you form the token. And of course, let's say this word, each word or subword token will have an ID for them, but it has no meaning to the machine. It's just an ID. So usually it will be converted to an embedding vector, which is a numerical vector, with vector containing multiple numerical value, and which contain more semantic meaning. You probably will have more semantic meaning related to the embedding vector. Is better because we prefer more better representation with semantic meaning, so that we can have better compute the associations or the relevance. Okay, then what? So these are just the words or the token from the language. So then we need to form the query, the key, and the value. So how does it form? So basically, you take the embedding vector. This is the embedding vector over here, and you will convert it to another vector based on this W. Okay, this a kind of a matrix that can convert your vector into something else. So each of them, so actually the token will be repeatedly, but multiplying by different conversion matrix, you can say. And this matrix is trainable. Okay, so what does that mean? We can think about this. So if you still remember, I talked about perspective, this keyword. So you can imagine this is something trainable, and that means it depends on your applications. Depending on what you are trying to solve, the model which would try to train or try to learn the matrix that related to the perspective you are looking for. Okay, you don't have to design your perspective, because during the training, the machine will be able to learn the perspective to look at your token, your embedding vector. Okay, so that's the key. So you can see that this is how you learn the perspective to look for. Okay, is that clear at this moment? And then let me just continue first before you ask questions. I need to finish this slide first. So once you have this QKV, so you can see here, this is the embedding, this is the QV vector, this is the key vectors. So these three are just computed with the weight equation Q, K, V. Okay. So this three will be trained will learn what are this. And then we'll have another value. We'll compute this. Once we have learned this, we're able to compute the QKV vectors. And with the QKV vectors, all you have to do is very simple. You just perform a dot product between the Q and K, and then divided by some scalar. So you will compute this value divided by this. Okay, something like this. So this is the dot product and divided by some here value, and you will get this. So you can regard this is the importance of this or relevance or attention score, something like this. But we will not just use the original value, because we're gonna normalize them with the softmax, so that this two value, if you have three value, you will make sure all them add up to one. So this is the meaning of softmax. So it's some kind of a normalization of the weight, the importance, or the associations. So once we have this attention score, we can basically perform a weighted sum. A weighted sum of what? Because we still have the value vector. If you remember this guy, we still have the value vectors. And we will multiply this importance, the ratio, the weight. You can regard it as some kind of weight, the importance of this to the value vectors, and then the form. So this is how you done. You see that? This multiplied to this multiplied to this. So you form this guy, and then weighted sum, which means you add them up together, and you obtain the final one. So this is how we form the attention. Okay, so here is a very simple idea, is just QKV, but QKV by looking up, this lookup mechanism is basically a dot product, and the value of the dot product will tell you how relevant these two items are. That's the idea. And we're going to normalize them so that they add up all equals to 1. Okay, that's the meaning of softmax. Okay, then you may ask, well, so far you are just covering linguistic example. How do we deal with image? So here I'm going to show you how this self-attention or attention mechanism can be applied on image. Let's say we have an image like this. We have an image. And of course, a single image doesn't give you a self-attention. We need to divide them into some kind of token. So one of the simplest way, I'm not saying this is the only way, keep in mind of that. This is one way to do it, is to divide the image into patches. Okay, each patch can be linearized, so you can divide them into rows and then concatenate them to form the vector, a linear vector like this. Okay, so that's one way to do it. Flatten them into a vector. And again, okay, so let me go back this. Again, all we have here are some RGB value, or just, let's say, just pixel. Pixel 1, pixel 2, etc., etc. Okay, so they are what? What are RGB value? RGB value are just color or intensity. they don't really have a more higher level semantic meaning. So it's not good for directly processing or lookup. And this is why we usually apply a projection matrix so that it will convert these pixels into something what we call image features, which containing more visual meaning. Okay, so this is called a visual feature vectors. Probably have the same dimensions as the original one. It doesn't matter, depending on your design. So here, although I draw it as a pictures, as a sub image or patch. Okay, even I draw it this way, it is not image. It is actually the feature. I just draw it, so it's this one. Okay, even I draw it as an original patch. So keep in mind that because I want to make it for illustration purpose, so I still keep the image. So these are feature vector, just like the embedding vector for the text case. Okay, then what? Then again, we have we want to take this basic feature vectors to compute the QKV vectors. And again, we need to learn the matrix, the 3 matrix, to convert. So this guy multiply this, okay, to calculate the attention, this Q vector. And for each other, we'll have the K vector with the multiplication of the WK. So we form the Q, the K, so these are K vectors, through this learned, these are learned, the matrix. And again, as you can guess, this learned matrix will tell you what perspective to look at. For image, there can be other kind of perspective. For example, whether maybe we have look at the texture perspective. For example, the castle in this previous example. If you have a subpatch over here and over here and over here, the texture may be highly associated comparing to the sky patch, right? And you can also have a perspective looking at color, a different perspective, or even look at the semantic meaning, something like a semantic meaning. Okay, more other kind of features. So, for example, spatial. From the spatial perspective, what does that mean? That means, for example, whether this patch and the other patch are next to each other or far away from this guy. So their spatial relationship, something like this. It depends on what you are looking for. So it doesn't matter what perspective. The machine will tell you, during the training, you will find a perspective to look at. But I have to tell you, sometimes this perspective cannot be interpreted by human. Okay, so sometimes you don't know why the machine will learn this perspective to look for your image classification applications or other applications. This texture, color, spatial stuff are just something we can interpret, but there can be some perspective that we don't understand what it is looking for. Okay, again, once you have the QKV, all you have to do is to perform the dot product. Like this. It's the same. And you get a relevance or attention value, alpha. Okay. But they are not normalized, so we're gonna make sure they add up equals to 1 through this softmax mechanism. So once we have that, the next step is we have this relevance, and we have the V vectors calculating with the learned matrix. So we have all these V vectors, value vectors, and then we can multiply them to form a weighted sum like this. Okay, so this is exactly the same as the linguistic example. It's just we are applying on image. So far, any questions? So I just tell you how it works on different application or different kind of input, how this self-attention work. So let's see if there is any questions. So far, no. So let me just continue in that case. So once we know how to compute the attentions, okay? Now we know how to compute the attentions, and we also know is looking at one perspective. Okay, looking from one perspective of your data. Maybe it's texture. Maybe in the linguistic case is something else, like whether the stuff is living or whether it's from the spatial perspective. Okay, that sounds like sometimes our problem cannot be just by looking at one perspective, right? And that's true. If you look at the image one, it's especially true. We can look at the texture perspective. We can also look at the color perspective. We can look at other perspective related to visual. And so that means the single self-attention may not be sufficient for most applications. And we call this the output from the single attention we call it a head. Okay. So one perspective is not enough. So we need multiple of them. We need multiple perspectives when we solve a problem, when we try to understand the problem. Multiple of them. In other words, we need multiple self-attentions, computations, each with different set of those learnable matrix, WQ, WK, and WV. So this is how it works. So this is a single attention computations. You can see there are one of them, there are two, there are three, and there could be more. So we'll combine each of them, each head, and we call this multi-head attentions because we're looking at the problem from different perspectives, multiple perspectives. That's the idea. So don't worry about the equations. The key thing here is that we compute. So here is just a single attention self-attention computations. We have the tokens of n dimensions, and then we're gonna convert them to the Q. This is Q. This is K. This is V. Okay, and because we have multiple tokens, remember we have a lot of tokens. So it's not just a single vector. There are multiple vectors of them. And this whole one is one head. Okay, we'll compute one head. Like this one. Because we take the dot product, softmax, this A, and use that to do a weighted sum of the value vectors. So this gives you one head or one perspective. To look at the problem. Next one. So because as I said, one head is not enough. We should have multiple of them. So this is one, head two, head N. I think this is N. It's not H. Okay. So we can then concatenate them So this is H1, H2, Hn, etc. So during this training, we'll be able to find what perspective to look for. Is that clear? So this is the basically what the most important stuff in transformer, the tensions mechanism, and we are looking at multiple of them, not just a single self-attentions. Let me see if there's any questions. Not so far. So let's continue. I'm sorry, I maybe overrun a little bit, but I'm close to the end. Okay, so this vision transformer, now we have talked about the key thing about transformer, which is the attentions. The next step is how you're going to apply on the vision applications. In particular, here is the image classification problem. We want to classify it. And this VIT was proposed in 2021 in this paper. For those of you who are interested, can take a look on that. But here I want to emphasize how they got, it's actually an applications of transformer for image classifications. So here, let me just the highlighter. So you only have the encoder. It doesn't contain the decoder. And of course, it is a multi-head attentions, just like what we have talked about. So since I have talked about how to take an image and apply self-attention, so you can see here, show P. So you can take an image, just like what I have said before, partition it into patches, and convert each patch into basically a vector through this kind of image features. And one thing here is, so these are the image features vectors. And you will add extra token, and this is learnable, a learnable one, because we're gonna use this for classification purpose. So it's basically, this flow is same as the previous. And we add one more. This is called a position embedding or positional encoding. What does that mean? That means you basically tell, oh, this guy is on the top left corner, and this guy is on the left, probably counting from the top is the second patch. Of course, it's not like that. The meaning of the position encoding is trying to tell or to label each of them. Where did you come from? Where is your position in the original image? Okay, so this is the meaning of position encoding. And then we can calculate we can just go through the similar mechanism as the QKV through this transformer encoder. Okay, you will get some results, resultant vectors, and you will also get this guy. So actually, we don't care what are this. We don't care about it. We only care about this, because this guy will go through an MLP, which is a fully connected neural network. So basically, it's not CNN, it's a fully connected one. That means you have multiple layer, maybe 3-layer hidden layers, and each guy are fully connected to everyone. So it's very complicated, yeah. So basically, you have every node connected to the other, every node on the other layer is called a fully connected layer. You should have seen it even in the CNN. Sometimes you can define a fully connected layer. But this MLP have only fully connected layer. You can say that. With this one, with this MLP and the input on this trained token, you will be able to do the classifications. So that's the whole idea. Very simple idea. It's just the same transformer for image, but we add extra token to help the classification purpose, like this. So this is the design of the VIT, and it has been shown this is a very effective one. And I think that's it for today. So that's a first demonstration of the transformer using in visual applications. Depending on times, I'm not sure whether I can cover this in the diffusion model, but I can tell you this VIT, this transformer approach, not just using for image classifications, it has now become a popular trend to be used in the diffusion model. So sometimes you see online people use a notation something like this, DIT. It stands for diffusion transformer, which is a application of transformer inside the diffusion design. So we'll talk about, I hope I get time to cover this, but if not, I still will cover the diffusion in the last lecture, 2 weeks from now. So I think I should stop here. Is there any questions so far? Let me just go back to see the chat box. Okay, no. So let's see the chat box. Any questions? Any comment or questions you want to ask? Just feel free to ask. You can voice out. You can also type in the chat box. I hope it's clear. If there is not something not clear, just feel free to ask. Everything good? If that is the case, I think we should complete this lecture at the right time. Now it's 11:50, so it's the right time to stop the lectures. And for those of you who have no questions, just feel free to go. If you still have any questions, feel free to stay and ask your questions. I will be happy to answer. And if nothing else, I will see you next week. Thank you very much. Okay, does VIT need more training data than CNN? I think it usually we don't. This is not really related, I think, because it depends on. It doesn't depends on your. I think the real question to ask is what kind of if as I mentioned before, transformer can achieve long-term dependency, which means if your problem require you to associate items that are far away from each other, I think you should choose transformer. It's not the case. I think you can use the same amount of training data to train both of them. And you see, instead of getting locality built in, let me just see what you're asking because it has to learn local image structures. I don't think you can always find use a CNN to solve the long-term dependency or the long-term relationship. This is more a fundamental limitations of CNN because you have the local kernel during these convolutions. I can only say the CNN is not good in handling long-term dependency or relevance between the items. That is the key problem of CNN. Um, Usually they use the same, you can use when, especially during research, they will use the same amount of data to train the DIT, to train the VIT as well as the CNN and do the comparison. But I think the right question to ask is whether your application really need data long-term dependency, long-term data associations. And CNN is certainly not as good as Transformer in this sense. I hope I answer your questions. So if you have any other questions, just feel free to ask. Okay. Another question is about the adversarial training. Will the model become more tolerant to noise, leading to lower test accuracy? Mm, I think depend. So certainly after the adversarial training, you will have a more tolerant, high resistance to this kind of noise. Certainly, it will improve. Whether you have a lower test accuracy, it sometimes depends, depending on the application. It's hard to tell, and it's case by case. One experience I have gone through is that at that time we want our model to be more robust to JPEG noise, and we have included that in our training. So you can consider JPEG noise is a kind of a adversarial attack, and we include that in our training. Our experience is it doesn't change too much on the test accuracy. It doesn't change the performance or lower the performance too much. I would say it's more or less the same. But the model after adversarial training certainly is more resistant to JPEG noise. So this is our experience, but it doesn't represent all the case. Thank you for your questions.